Today we're going to build a machine that uses this pneumatic cylinder to operate this hand depaneling tool. Welcome back to Cloud 42, I'm James. About 6 months ago, I did a video showing a little Hakko hand PC board depaneling tool, and I showed how I used that to separate out the electronic leadscrew PC boards from the panels that are used to manufacture them. Now, since the time I put that video out, I have cut out literally hundreds of PC boards using that tool, and I'm getting kind of tired of doing it by hand, and I think it's about time for an upgrade. Now, there are commercial solutions available. There are machines that you can buy that separate PC boards in all kinds of different designs, but the one thing that they have in common is that they are all industrial tools, and so they're very expensive. I am not looking to spend a lot of money on this, so I had something a little bit different in mind. Now, if you want to see more about this tool, you can go back and find that. There will be a link in the video description, and probably I'll put one up here in the corner too. But I have separated literally hundreds of these boards out of panels. And one of the things that becomes evident really quickly is that a tool like this was really not designed for production work. This is great for a hobby shop. If you got a couple of panels, it's great. But after a while, the little cutoff pieces start sticking down in the throat of the tool, and they jam it up so that it doesn't open. You have to physically put a finger behind it and force it open. And so you're constantly going like this, pulling with a couple of fingers, and it's constantly hitting the back of the finger you're going to use to extend it. And so after you've done 100 of these PC boards, you end up with a bruise on the back of your finger. And so I want to upgrade this to something better. There are tools that you can buy, little machines that use pneumatic power that sit on the desk and have a blade coming out the top, and you go chunk, 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 and you can just run your tool through it, or run your PC board through it. And I want to try to make something like that. They start around $500 or $600. I'm not in the mood for that. I have a tool here, and I have a pneumatic cylinder. And this is just a small pneumatic cylinder, double acting. And I believe in a previous video you've seen this. I was using it to test some pneumatic valves. And so what I want to do is rig this up and design some kind of fixture that will hold the pneumatic cylinder and will hold the tool so that the pneumatic cylinder can actuate the tool. So this has got nice rubber grips on it that are great for using by hand. But if I peel those off, underneath, it's just, ow. Yeah, okay. There's a little spring in here too. If you pull the handles off of one of these, be sure and remove the spring as well. It will bite you. This is just a stamped sheet metal tool, and it should be relatively easy to build something that will clamp onto this handle and provide a means to mount a pneumatic cylinder with a rod to pull through and pull on the other handle. So I think the first thing to do is to go into the computer. Now, I have already designed a little machine and fixture to hold this, but let's go into the computer and I can show, I'm not going to do a full tutorial, but I can show some of the details of how I did the modeling and how the thing is going to work, and then we can put it together and try it out. This is Fusion 360, and this is the design that I ultimately came up with. And you can see I've got the pneumatic cylinder mounted with a pull rod so that it pulls the handle of the hand tool. Now, in order to design something like this, I started out by just drawing up and modeling the parts that I have that I'm going to start with, the pneumatic cylinder and the tool. Now, the pneumatic cylinder is easy. Just took a caliper and took the measurements and modeled this up. These are mostly nice chunky solids, cylinders, discs, rod here with a thread in the end, and I went ahead and modeled all the flats, everything except the ports. I didn't bother with that, but I have all the attachment points so that I can just use this in the model and design around it. Now, the hand tool is a little bit more difficult to model because it doesn't have regular polygon surfaces. It's not, cylinders and rectangles. Everything is curved, and this part is made from stamped sheet metal. So the way I went about this is I started with a photograph. Now in Fusion 360, you can come up here to the menu and say Insert Canvas, and you can just insert, you can load a photograph. So insert canvas, say insert from my computer, and you can load a photo. And that's the first thing that I did, is I just laid it down on a desk, held my cell phone on top of it, tried to get as square as I possibly could, and just took this photo. And then once I had this photo, I started overlaying it with sketches. So I laid a sketch on here for the fixed part of the jaw, or the fixed part of the tool. So this is the part that I've been considering fixed because it has the anvil that the cut occurs against. And then the other part that's sandwiched in there, I guess I can't twist this, it's just a flat photo, that has the moving jaw is the moving handle. So I just took and created a sketch, and in this sketch took spline curves and just laid my points and zoomed in, and as carefully as I could just drew a line around the edges of the part. It's important to get this as close as I could possibly get it, because ultimately I'm going to try to make a 3D printed part that this handle will fit into. And did exactly the same thing for the other jaw. Now, a couple of notes, and so here's the other part, and so I have a separate sketch for that, so that ultimately I can then extrude those as solids and turn off the canvas and actually end up with a model of the tool. Now, let's talk a little bit about scale. So when I started out, the very first thing here with just the one sketch and the canvas is that when I brought in the image, this was not to scale. The image is just whatever scale it happens to be imported. So what I did is I did a couple of things. One is there's a setting. If you come up here to the name of your account, click on that and go to Preferences. This brings up the Preferences menu, and under Design, there's an option here called Scale Entire Sketch at First Dimension. And this is off by default, but I turned it on, and what that does is it allows me to draw a sketch like this and then come back and put one dimension in it, and instead of distorting the sketch, it will scale the entire sketch to that dimension. So once I had put this in here, you'll note that my sketch is centered around the origin here, and that's because the image comes in centered around the origin as well. So that if I scale the sketch and I scale my canvas by the same amount, they'll stay on top of each other. So what I did is I came in and found a dimension on this sketch that was really easy to measure, and it's from this point to the furthest point of the handle. And I drew a construction line, and then I threw a dimension onto that. And as soon as you click to put a dimension on there, you can see that it's showing me the current dimension before I even place it. In this case, it's 129 millimeters, because that's what was actually measured. Now, when I first clicked on it, of course, it wasn't 129 millimeters. It was like 65 millimeters, or whatever it happened to be. So I wrote down that number, and then I set the dimension to the correct size, and that caused the entire sketch to scale so that now my sketch matches the actual size of the physical tool. Now, of course, the sketch, once it's scaled, no longer fit the canvas, but since I know the size, 129 that I scaled it to, and I know the original size that the sketch was drawn at, I can figure out the percentage that it scaled the sketch up or down. And then I just went back and edited the canvas by double-clicking on it, and then came in here to Scale X and Scale Y and just entered that percentage, and it scaled the canvas to match. So that got me to this point where I have a sketch that's the actual live size, and then I could go ahead and do the other sketches and model out the tool. And so that's what I did, and turn the canvas off here, and ultimately modeled out the entire tool and did my best to actually model where it's bent here just by layering this up and putting in fillets and curves and chamfers. And I tried to model all the other parts on here. There are little pins that stick out. There's a rivet that goes through. There's a little hole here. And of course you have the pivot up here. And then actually modeled the motion by creating joints between the components. So I actually have the motion, and I did my best to get it as close to the actual dimensions as possible by, like measuring across it when it's open and when it's closed, and looking at kind of where things line up and where these edges line up to try to model as closely as I possibly could to the actual physical action of the tool. So now that I have the tool modeled and I have the cylinder modeled, I can just bring those into a new assembly. And the first thing I need to do is figure out the physical relationship between where the cylinder is going to mount and where the tool is going to mount. And I know a few things. I know that the stroke of the cylinder is 3/4 of an inch, and I know the angle that I put on this joint when I constrained it. So I know how many degrees this tool moves through, and I know the stroke of the cylinder. So it's a relatively straightforward thing to just build a sketch. And I've built a sketch here with a line that starts from the pivot point and comes down to the center of the handle. And then I have another line that comes down and I have this constrained with the correct angle, so that the angle between these two is the angle between the open handle and the closed handle. Then it's straightforward to come in here and put a dimension across these 2 points and say, got the wrong sketch open. Let me open the other sketch here. It's easy to put a dimension across these 2 points and say, this is 3/4 of an inch. These two lines are equal length. And I have a dimension here of 23 degrees, which is the difference between open and closed. And Fusion 360 will then automatically make these the correct length. And once I have a line drawn between those, I have the line that I want to connect the cylinder. I want to have the cylinder in line with that so that it's pulling on this point of the handle, and pulling 3/4 of an inch will completely close the tool. And so once I have that, I can start constructing, and I can move that cylinder into the correct position and start to work out the rest of the connection. So in this case, I've got the cylinder where it needs to be, and I've started drawing in the arm. And then ultimately, I'm not going to go through this in detail, go through and design a clamp that's going to go over that. And once we sort of get that geometry figured out of how I'm going to have an arm that pulls it, then I can go about building a frame to hold all the parts. So I kind of drew up a flange and then started drawing some kind of chunky rectangular shapes that have a cutout for the handle, and then also provide some support up here at the top. So as this piston pulls back on the handle at the angle we determined, the tool will be supported. And then ultimately, sketched out, started making some openings in it. And ultimately, let me just jump all the way to the end here. Have a clamp plate that goes on it, figure out all the hardware that's going to hold everything together, and then put a plate on the bottom and put in some fillets so that these aren't sharp corners. They have lots of plastic material in here to support the pieces, and so that it won't be brittle. And once we've got this, we're ready to 3D print the parts. Now, there are some things about this that are kind of interesting. If I come back and turn off a bunch of the things here and leave just the frame. The frame is by far the most complicated part here to print. So this is the frame. And as I designed this, I had to think about, how is this going to be printed? I have an FDM printer, meaning that it's going to be using filament and depositing material in layers. And as this thing is built up, I can't have extreme overhangs. I can't have things that just start out into space at a 90-degree angle. I have to think about that as this is designed. So for example, you can see this facet here. As this part is being built and we're coming up in layers, if this just stepped out square, like the top of this is square and level and the top of this is square and level, if this were square and level, then as we're printing, all of a sudden the printer would be trying to print out into space with no support. So I came in and put a 45-degree angle on that so that it will come out gradually and gradually print that overhang as it goes up. Same thing here. I had to think about all of these angles. This overhang angle is pretty extreme. My printer can actually handle that just fine, and I know that, but I have to think about that as I'm designing the part. So an easy way to do this is I'll just pick this surface on the bottom and say Inspect Section Analysis. And this allows me, let me do it the other way around. So let's choose the top surface here and say Inspect Section Analysis. And then this allows me to examine the model slice by slice as it goes up. And so I can come in here with an eye for, is the printer going to be able to build this? So here's a place where the printer is coming in, is going to have to bridge. That's pretty small. That's going to work. Same thing here. We may have a little bit of trouble right here, but it's going to come together and bridge pretty quickly. And from there, the printer should be able to build that up. And as we go up, we can kind of examine this with an eye for, are we going to be able to print it? And so here's a place where we're starting to come out and build with an overhang. Over here, we're starting to come in here with an overhang, and as this gets closer and closer together, this overhang is going to become increasingly difficult. So we should expect a little bit of trouble and a little bit of drooping there, but it's going to come together pretty quickly and then bridge across, and then it should be fine. And then as we continue building, this spike that's building out is going to be a little bit problematic, but I think it's going to be all right. I think there's enough material behind it, and soon enough we get up to a point where it's going to connect, and once we've bridged, we should be in pretty good shape. In any case, this edge on the bottom here is not a functional surface, so if it ends up being a problem and it droops a little bit, I can just slice out the plastic, have learned a lesson, and move on, but I think it's going to work okay. And then we build up the rest of the way, and the rest of this is easy. So I think this part, again, because of careful design and because of, work like putting in this facet and carefully controlling these angles, I think this part is going to be printable. Let's send it to the printer and see what we get. Okay, I have all of the parts printed, and they turned out really well. I'm very pleased with the way this printer is tuned and working. This is, by far the most difficult part to print because there's a lot of overhangs, there's a lot of unsupported area. In terms of print quality, it looks like we've got a little bit of goober right down here, and this is again just a place where there was a lot of overhang, and the corners were starting to curl slightly as it printed, but as you can see, it easily recovered from that, and the rest of the print up here is very clean. In the place underneath here where it was unsupported and it had to bridge across, there's just a little bit of stringing, which is totally to be expected. We can clean that up. For this kind of stuff, it's really convenient to just use one of these Noga deburring tools, and you can easily just get in here and just like that, clean off any plastic. And in this case, it's just aesthetic, and I just want to make sure that nothing is going to be in the way when we go to bolt the cylinder on there. And the rest of this is pretty nice. And for those of you that in a previous video gave me a lot of grief about the top layer looking bad on this tap guide, that is true. And the reason is because of the complex geometry and the high speed with which I was printing this. Because I was trying to go 100 millimeters per second up here, and there's all these stops and starts and little gaps in the extrusion, the top surface of this ended up being kind of a mess. But this is the same printer, same roll of filament, and you can see that that top layer is actually quite nice when you're not constantly trying to stop and start. There was some suggestion that the reason that this looked bad is because I was overfilling the top, and that's not actually the case. As I mentioned down in the comments, I actually slightly underfill is how this printer is tuned, so that you get a nice smooth surface that is as close to dimensionally accurate as I can get from the printer. And so if you look at this under a microscope, there are some small gaps between the extrusions. They don't come flush and smooth on the top, but it does leave a nice, flat, smooth mechanical surface that's great for mechanical models like this one. Now, I left a 1/4 millimeter on each side of the groove for this handle, and again, the handle was only measured just based on a photograph. I never actually took any measurements across it with calipers, but it actually ends up being a very nice fit. That fits in there, and it goes in easily and comes out easily, but there's just enough grip on it to hold it in place. So that's exactly the kind of fit I was looking for, and then we'll put the clamp plate over that to hold it in place. And let's prep some of these parts. Now, the holes here are 1032, and I actually modeled the threads into those holes, but there's no way that a 3D printer with a 0.4 millimeter nozzle is going to effectively build a thread that actually fits. So if we grab a screw and try it, it will be a little bit tight. And it'll kind of start to go in, but I don't want to split the model, so I'll just go ahead and run a 1032 tap through all of these holes. And since the threads are already in there, it actually goes very easily because the threads that are modeled into the part and 3D printed are enough to guide the tap cleanly. Okay, that's that. Now we have a similar situation in this part, in the pull arm. These are 5/16 18 threads in here, and needs a little bit of cleanup because of the overhang, same situation we had here. And I'll go ahead and scrape that out with a knife, and then we'll run a 5/16 18 tap through it. Now, this is a form tap. It's the only 5/16 18 tap that I have. And because this was printed and the layer lines are across this direction, I'm a little bit concerned that it's going to split. So I'm actually just going to clamp this in a vise lightly in this direction to take up that force while I run the tap through it. Now this would be a great opportunity to use that tapping guide block, except that since I 3D printed threads in here, this is already just grabbed and lined up, and there's no need to no need for a guide block to straighten it because there's already threads in the part. The only other thing that I want to do from a prep standpoint is any of these surfaces where a screw needs to go through that were printed down on the surface of the bed, there's sometimes just a tiny little bit of squeeze out, and so just running a countersink in there just ever so slightly will clean that up and make sure that the screw will fit easily in the hole. Okay, let's put this together. So that goes in there, and then clamp plate goes on top with 3 1032 screws into the holes we just tapped. Okay, that looks pretty good. It's nice and solid, and since the pulling force is going to be back in this direction and we've got good support behind here, I think that is going to work well. Now I left the depth of the slot that handle goes into 1/4 millimeter shallow, about 10 thou, and that seems to be enough. The plate that I put down on top of it is flexed slightly, and it's providing that clamping force. Okay, now we just need to mount the pneumatic cylinder, and we'll put the arm onto it first. And I just have a 5/16 18 stud. This is just a piece of bolt that is cut off and faced. We'll put that into the pull arm first, and then we'll screw that into the pneumatic cylinder. And to tighten this, I will use these flat jaw Knipex or Kniepex pliers because they won't mar the surface of the cylinder piston. And then we'll just slide this in and put in the screws. And these are 10/24 screws because that's what the threads are that are already in the cylinder. And the major force here is going to be pulling the cylinder up against the flange so the screws don't carry too much of the load. Okay, and so that's in place, and we've got our pneumatic cylinder motion here. Now we just need to put the clamp on. Now the clamp is printed with flexible material. This is actually Ninja Tech Cheetah, and I wanted to use a flexible material for this because I was a little bit concerned about the shock loads as this piston slams in and out, and I just wanted to make sure there was a little bit of compliance here, just in case we ended up bottoming out the tool before we bottomed out the piston, because I wanted to make sure that we weren't going to put too much shock down on this thread that's just threaded into the plastic part. Now, sensitive viewers should probably look away now because I am switching over and mixing Imperial fasteners. These are M3 screws. I'll just run these through and put a nut and washer on the back of each. And there we have it. Let's hook up some air and see how it works. Now I already have a pneumatic valve pre-plumbed for this. Now this is an electric valve. Ideally with a tool like this, what I would really want to do is just have a pneumatic foot pedal to operate it that actually has the pneumatic valve in the pedal. I don't have one of those. I went out to Automation Direct to order one, and they were out of stock. They're actually in stock now, but that doesn't help me because that's still a week away from me getting it. So I just grabbed an electric valve that I had laying around from one of my previous videos. And this is a double acting valve, so the air comes in the pressure port and can be diverted to either side of the piston to press or pull, depending on the position of the valve. And then I have rigged up an electric foot pedal switch that I had laying around that I will just have on the floor and use to activate this valve. Let's go ahead and plumb this up. This uses push to connect fittings with 1/4 inch line, so it should be real easy to connect up. Okay, power supply is set to 24 volts. Switch on the power, get my foot down here on the switch and press the switch. And I guess, you know, unsurprisingly, it works. So I guess the only thing left to do is grab some PC boards and test. Before I actually grab a PC board, there's a couple things I want to do. I would like to anchor this down because if I'm working up here feeding a PC board through it, I want to make sure it doesn't move around on me. Grab a couple of clamps here, and I'm just going to clamp this down to the bench. And then the other thing I want to do before I bring out PC boards, this is a grounded workstation. You can see I've got a grounding wrist strap here, and I don't want, because I've got, you know, pneumatic, I got air moving here and I got plastic, I want to make sure that I'm not building up a static charge. So I'm actually going to ground the metal parts here. And I've just got a alligator clamp here. I'm hooking it to the ground on my ESD mat, and I'll just clamp that to the metal of the tool. There is a black oxide coating on this thing, but I'm not worried about that. I'm pretty sure we're going to get enough of a connection to drain electrostatic charge. And then I'll go ahead and, this is probably a complete overkill, but I will go ahead and hit one of these screws just to make sure that the metal of the cylinder is actually grounded as well. And the goal here is just to make sure that we're not building up an electrostatic field because of the plastic in this tool that will then, you know, potentially build a charge on the metal point of this tool, so that when I feed the PC board in, I end up discharging into the circuitry. Okay, let me move the cameras a little bit so that you can see better and get a PC board, and let's try it out. Okay, I've got the cameras moved around here, so I've got a nice close shot of the tip here, and you can see the action. It's just pulling the handle. It's just like a little nibbler. Let me grab a PC board panel and let's try it out. Make sure I've got my grounding strap on here. Just slot it into the tool and press the pedal. And that is all it takes. It goes right through. That is way easier than doing this by hand. These grooves through the center between the PC boards are a little bit narrower than the ones on the edge, so it seems to work best if I lift it off. Okay, I am extremely pleased with that. That is way quicker than doing it by hand, and after separating that whole panel, the back of my finger doesn't hurt at all. So this has definitely solved that problem for me. I had been thinking about doing this since I first got this hand depaneling tool. I really wasn't sure how it was going to work out, which is the reason why I didn't try to machine an aluminum tool for this. I wanted to just start out with 3D printed parts, see if the concept worked. Work out the geometry, figure out if this is the right size cylinder, figure out how much air pressure it was going to take. Incidentally, I'm running this at about 45 PSI. I did a little bit of testing. 30 would cut, but it wasn't enough to cut reliably through the PC boards with the perforations. 45 is enough that it cuts through those reliably, but if I take a solid strip of PC board and try to cut it, it makes stress marks and actually distorts the PC board a little bit, but it doesn't actually cut through. And I'm happy with that. That's kind of what I wanted. I don't want to put any more pressure into this tool than I have to, both for safety reasons. 45 pounds, if I get my finger in here and the thing crushes it, it's going to hurt. But it's not enough force to really injure me severely. I could take a little nibble out of my fingertip with the end here, but nothing that's going to be a serious injury. So I'd like to keep that pressure down. Also, because I'm pulling through a threaded stud into a plastic part down here, I'd like to minimize the amount of pressure. So if the tool actually jams and can't cut, I'd like to limit the amount of force going into that joint just so this lasts longer. Now that I've got this worked out and I'm sure the geometry is good and I'm sure the tool works because I've just demonstrated it to myself, I could go back and make this part out of aluminum or some other metal to make it more durable, but it's working fine. I've got a bunch more panels right here. I've got the tools set up and ready to go. I'll go ahead and run them through and we'll see how it goes. And if it works and if the tool holds together, then I really don't have any reason to make a metal one at all. I'll just continue operating with the plastic one until it breaks. And if it breaks after 100 panels, then who cares? I'll just 3D print another one. And if it doesn't last very long at all, I can switch to metal. But in terms of a shop expedient tool, this worked great, and I'd best get on to the rest of those PC boards I have to separate. If you enjoyed this video, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.